a good thing, I guess. Alrighty, here we go. I'll wait like 12 more minutes and we'll get started. Alright, so just quickly, you can go on to mentor.com and send a code asking questions while the talk is going on. And then that way we'll come to questions at the end and we'll just answer as many of them as we can and get to the top of like most uploaded ones. Yeah, so I guess let's get started. So we're going to be learning classes in Scala, case classes, companion, singleton object, and trace. So we're going to be keeping it relatively basic. I've kind of aimed this to be, I guess you could say, a low spiciness and easy talk for people who are just getting used to Scala and they want to learn. They might have some background in Java, so the analogies, some things that happen in Java, but also try to explain some general object-oriented concepts in here for people who might not be familiar with that as well. So we're running with a bit of a metaphor for the length of this talk. So you've been hired by a llama shaving company, and your job is to create the concept of a llama. It should store its fluffiness somehow, and it should be able to be shaved, reducing its fluffiness. So let's kind of just whiteboard this up like a very basic, I guess, object-oriented stuff. So just crash. So those of you who are familiar with object-oriented, you already know you can create a class. So we can create a class llama. And then on that class, you can attach fields. So I can make a field fluffiness. Define that as an integer, and then I can make a method on that, like a function, shade. We can take in an int to define how much to shave off that llama. So all pretty basic so far. It's also worth mentioning this class was static, and then we're able to create objects of that. So we can create something like one using a new work. So we'll jump straight into showing how that's done. Scala. So you got your basic class in Scala, pretty straightforward, just class llama. And then creating an instance of the class, also pretty straightforward. So we got our banana llama, yeah. And you can just say new llama, and then there's nothing in it, so we've just got empty places there. So adding a field to the class in Scala is fairly straightforward. We're just adding fluffiness and specifying that it's an int. And we're able to create that, okay, we create a pajama llama with new llama 1. So that'll give it a fluffiness of 1 when it starts. And then we're able to access that field. So we can go pajama llama dot fluffiness. Now, this won't actually work. So why that won't actually work was because fluffiness was declared as a private value in there. So describing it as a val allows us to access it out of the class. By default, when you declare things like this without putting val in there, it's declared private, and that means you can only access it inside these curly braces. So this is all basic stuff that you'll see in Java and a few other object-oriented languages as well. Now, we can add in our shave by saying define shave, takes in a wool amount, an integer, and returns unit. So unit means nothing here. And it's saying that it's not going to return anything, and that's because we're going to try and modify fluffiness. I'm going to say fluffiness is equal to the original fluffiness, take this raw amount, and reassign that on fluffiness. That won't work either. So what's going to happen is, yes, it's immutable. So immutable means it can't be changed once it's declared. And it's done by that, done like that by default. So Scala does this to keep things functional. Functional programming, in functional programming, we always keep our variables immutable. So now let's return to llama. So it's now actually going to return a llama in here. And that's a whole new llama that we're going to create. So we're going to say return new llama and then declare it with our new fluffiness technical amount. And there's a few things that Scala does here that's pretty nice. You don't actually have to include the word return in there, because Scala will always return the last line of any function that you do. So we can take return out of there. And then secondly, we can remove the curly braces there. And that's because it's only a single line. You don't actually need to declare it out of the function. You can just say it is equal to just this one single line. Now, we can use that method by just saying something like drama llama.shave, and that'll reduce that drama llama by 3 fluffiness points. And we create a new value there, shave llama, and then we're able to print that out. You can see that it will print 2 as its fluffiness value. So it's all pretty straightforward so far. We made a class with a field and a method. So class is just a schematic to make more instances of itself. We've seen some basic syntax, and we've seen the Scala is keeping things functional. So on to the next step. Let's turn it up a bit. Mergers and acquisitions. We've succeeded in a hostile takeover of the llama transport company in the Andes. So our llamas are now transporting goods on perilous journeys through the Andes. And you've been asked to add more fields. So we're going to update the llama class with strength and a name. So strength kind of defining how much they can carry. And we're going to create a copy of llama before they leave on their perilous journey. And then we're going to check for equality. So ensure they're the same as their copy when they come back. And we're doing all of this because we want to know that our llamas haven't lost fluffiness or strength of their long and perilous journey. So we can update our fields. We can update it by adding on strength and name in there as well. And then we can define copying and equality the long way. Wow, okay, so there's a lot of code there. Would urge you not to try and read it too hard. So what's happening here, we're extending clonable, we're defining equals, and then we're defining clone and doing a whole bunch of other stuff in there. Now, if you were doing this in Java, this is how you would do it. But we're not going to do that, actually. Instead, we're going to define copying and equality with one word. So, okay, what's the word that's changed? Case. Case, yeah. Easy, right? All we did was add case. Something else changed in there as well. We also removed val from a bunch of those things. So this is something called a case class. This is a kind of fundamental concept in Scala. So what is a case class? Well, you can think of it as a package for data. So it could be thought of similar as a struct from C, or maybe a JSON. And it gives you stuff you might want for data. So there's lots of things in here, such as being able to encode for equality, copying, getting hash codes out of them. ToString is implemented as well. It's easily serializable. You get pattern matching and algebraic data types, and finally you get automatically defined getters and setters. And that's why we removed val from there, because we now have a getter for those, and they're no longer private, so to speak. So how do we actually use case classes? Well, you're able to create a case class like this. It's pretty much just like creating a normal class, except we've now dropped the new keyword. And that's kind of I guess, a thing in a philosophy of it's now just a package for those 2 pieces of data, strength 5, fluffiness 5, and that third one, the string of its name, then it'll be Alabama llama. So copy llama. So we can create a new llama and go llama Alabama llama.copy. So that method there is automatically being implemented for us, and we can just use that. And the same goes for equality. So we can check if the Alabama llama is equal to the copy llama, and that'll still print through, and it'll just work just like that. So in summary, why do we actually have case classes? Well, they're good for storing data, and we indicate to people reading the code that it's a data type. Like this is my little package of data. This is where I store my stuff about llama, for example. And we get a lot of other things for free that you would want with data in there as well. So for example, we can wrap an integer with a miles or kilometers case class. So we get something like equality for free. So I might just quickly demonstrate something. So say you've got a space probe and it's landing on Mars. It's based on a real event. So it's landing on Mars and it will need to deploy its parachute 10 kilometers up. And so you define this as an integer. And then you have another integer over here, is your actual distance from the distance of the surface. So you can say maybe that's 100 to start with. And then it's rapidly dropping. The space probe is flying down towards Mars. So it's going down, to 90 and so on. And you're checking this for equality. Consistently, you're checking over and over. And as it goes down, you go, okay, right, finally we've reached 10, let's activate our parachute. But this was actually miles, and this was kilometers in distance. You just activated your parachute way too late, you're going to crash. You didn't realize that was going to happen the whole time. So a nicer way of doing this might be to create something like case class kilometers integer. And you wrap it in that. It's literally just an integer, but you wrap it in that. And now when you go to compare equality, and this one is also case class miles, just an integer inside it. When you compare equality, it will balk, it will break, and it will say this doesn't work. So you get back an error on that, and hopefully you don't crash your space probe because you're able to tell that something's actually going on in the first place. And of course, if you actually just type in the code kilometer and declaring your your that should be case class. Yeah. So if you're declaring that as that way, you'll be able to see the declaring quality here. As well. So there's a higher readability as well. All right, so quick recap before we move on. We've added more fields and we've turned Llama into a case class, which has given us a variety of benefits. So moving on, we now get requests for llamas coming in words. So you've been asked to create a llama object from a string. And an example of that might be, I want a llama with strength 3 and flopiness 1. So let's build a function that makes a llama from a string, a constructor. So declaring, you can just go ahead and declare a function like this, create llama from request string, and have it just return a llama. Notice how we can name this function whatever we want. That's going to be important later. So pattern matching. So this is another common concept in Scala that I'm just going to cover here. What we're actually doing here is something similar to a case statement. Who has used a case statement here before? Okay, so a fair few people. Jeez, put your hands up a bit more. Okay, all right, sure. So this is essentially saying, take that string request and then match it on a case. So what we're actually doing here is checking for equality. So I say, like, for example, is this string equal to, I want a llama with strength 3 and flopiness 1. And then from there, you can return a llama, instantiated llama there with strength 3, flopiness 1, and I'm going to call it Palmer. And then you can keep doing this to cover a whole bunch of cases, so on. And then what do you do when you get to a case that you don't have something matched for? So, sorry? Wrong. We could. So, okay, so let's think about if we return null. If you were in Java or something like that, that might be the right way to go. But in Scala, we try to avoid returning null because null has a bunch of problems. You get a lot of null pointer exceptions. In order to avoid that, we use something called option. So I'll just quickly explain option. So an option can wrap whatever you want. That's what the wrapping in Scala. So imagine you have your llama, and you can put that into a box. You can put that into a box, wrap it up, and send it off to someone. You're kind of mean, though. You might just decide you're not going to send anything in that box at all. So it kind of becomes a mystery box. It's kind of like a Schrodinger's cat deal, where you've got llama may or may not be in a box, and you don't know until you open it. And that's what it is with an option. It's either going to be, when you open that option, you're going to get out a llama, or you're going to get out a none type. Now, the none type is basically the equivalent of null, but it comes with a bunch of, because we're using option, it comes with a bunch of benefits in the sense that the compiler will check if it's possible for you to get to a point where you've screwed up and you're going to crash. So you get a compile time error instead of a runtime error later on. So I'll just quickly show what options are in code. So the first thing I've done here is I've wrapped llama in an option, just like that. And then I've declared this as none, which is basically the equivalent of null. And then I've gone through and I've wrapped these in sum types. So sum is the wrapper to say that yes, there's definitely going to be something inside here. Now, where does this function go? The function that creates new llama. So this will go into something called a singleton object. So singleton objects and objects in Scala, you've got to think of them as basically the same kind of thing as, remember before we had llama, and then we were able to create something from that, and you could say the new keyword, llama1. Well, this is very similar to that. So I can create something in here, make it the Dalai Lama. So we've got the Dalai Lama in there. Now the Dalai Lama is special. There's only ever one Dalai Lama, right? So if you try and create a new Dalai Lama, it doesn't work. So instead, you've got to, you basically just have this Dalai Lama. There's never zero. They always exist, but they're created from the beginning of the program, and then always exist throughout them. There's only ever one of them. So it's done just the same as a class, where it's got fields, and you can put whatever fields you want on there, and whatever methods you want in there as well. But it is otherwise just a single object. It would be the equivalent of saying, llama, and then creating one llama, and then throwing away that original class. Yeah. Okay. So declaring an object looks like this. This is the syntax. So it's pretty straightforward. We're going to create a llama creator object, and then we're going to chuck all of that back into there. So that's all of that code is all the code that we were just defining before in that function. And we put that inside that object. Now let's use that object. So we can declare a value. So here we're going to declare our value option llama, and we're just going to specify the type that it's definitely an option llama. And then we're going to use llama creator dot create llama from request, and then we can just put a string in there, and that will just work as it will. So there's a problem with this. The llama creator is rather separate from llama right now. So this could be kind of confusing, and there's a solution to this problem. So like llama creator is sitting in a whole separate file and everything. It might be somewhere else in the program entirely. So we're going to use something like a companion object. Now, a companion object is a singleton object, and it has the same name as its class, and it's in the same file as its class. So those are kind of the only two differences in how you implement it. And then it'll do some things on the hood in terms of privacy. It'll allow that companion object to access things in its class as well. So let's kind of see what we're doing in code to create a companion object. So here's our case class llama. So you can see in there, there's the shave definition. I've just kind of squished that away. And then we've got our object, llama. So we're now declaring it just like the llama shaver, just called llama. And then we can just add the method in there. It's pretty straightforward. Now it's a bit nicer because it's in the same file as our case class. So calling it works exactly the same. It's just you're now typing in llama with a capital L. And then you can just use that as it is. So summarizing case classes and Singleton objects. Basically, Singleton objects provide a way to store static functions. Does anyone use C# or Java in here? Yeah, it's quite a few. So, I mean, static functions, for those who might not have used it, it works a bit like maybe a function in C or something. The thing is, it's not attached to an object, what I'm saying, and it just takes in all of the information it needs. You can't access anything else. Now, there's another question, why not just have static classes instead of having objects? So in C# and Java, we do have static classes. So I want to try and answer that before I jump into it.
With how they get sort of initialized when starts.
Well, there's I guess the static classes work just kind of like C code. So when you have an object instead of a static class, you can actually extend the object and you can inherit from it, and you can do a whole bunch of other little things you would basically get with any other object in Scala. So it makes it a little more object orientated in that sense. It's kind of, I guess it's a little complicated to get into, but the static class has a few limitations that it might not have. Yeah, so there's a couple of benefits of Singleton objects. Why do we have companion objects? So this is generally because it makes more sense to a human. So a human can see that it's right there in the same file with the same name. That means it's related, right? But it also does a few things under the hood, like accessing those private fields and methods. And it's great for putting constructors in it. So you can try and put constructors in your case class. This is hard. It doesn't, there's a lot of limitations with it that I don't want to get into because it takes forever to explain them all. But being able to name your own constructor, put it in a companion object, and do it that way is pretty nice. So why do we have a constructor and a companion object? Like I just said, you can name it what we want, and we get more flexibility in what we return. So if you actually have a constructor in the class, all you can return is a llama. You can't return an option of a llama, you can't return a list of llamas, you can't do anything else in that. You get a bit more flexibility putting it in there. All right, so we're going to get a little bit more spicier. So getting into the final stretch now. We're monetizing the llamas further. So we've taken a contract from a French fashion company to advertise hats. So all of our llamas now wear hats. We've got the Paris hat, the Toulouse hat, the Marseille hat, and the Nice hat. So each hat requires a trick in a couple of seasons. We've got sit, shake, talk, and triple back. So what your end result should look like is print line hat.trick, and it'll print out something like talk. So let's think about this. All llamas must have hats, but a hat can come in 4 different flavors. So there are a few different ways of doing this. Each llama could store a string that describes the hat. This should probably set off some alarms. Why is it bad? Well, you could receive any input, like illegal hat, and then we would have a runtime error instead of a compile time error. So that means the program's going to crash while it's running, and it just received a string that says illegal hat. It doesn't know what to do with it because your logic only specified those 4 hats, instead of a compile time error where it can foresee that that's going to happen. So you might try and do enumeration instead. So some problems with enumeration. I want you to focus on number 2. So number 2 is that there's no exhaustive matching check during the compile. You still won't get that holy compile time error coming with it. So we're going to introduce something called traits to try and solve that. So trait hat is how you introduce it, like just declare a hat trait. It's pretty straightforward. And we now have a hat type from that. So we can now say our hat is defined as hat. Now we can extend that trait. So we're going to introduce something new here as well, case object. I'll explain it in a second. So our first hat, the Paris hat, extends that trait hat. And now we can define a value hat that is a case object Paris. We can extend this trait further, so we'll fill out the other ones in there. And then we can define the rest of these, Toulouse, Marseille, and Nice. Now, what is a case object? So it's all the same things, case is the class, but we do it to object. So you may have noticed case class implements equality and cloning. Well, there's only ever one object when you declare it that way. So it's a little less. We don't need stuff like that anymore. There's only ever one. But we want a pattern match. So we're still going to declare it as a case object to get that pattern match part. So let's go back to our hat trait and actually implement that pattern match. So we can define a function trick, which returns a string, takes no values. And then we can do a pattern match here. So you'll see it says this there, that this is referring to the hat that you've actually instantiated, like the Paris hat or something like that. And it says match that hat. And now you've gone and said case Paris. So if it's a Paris hat, it'll be equal to that object there, and then it'll return the string sit. And then we can implement that for the rest. A little bit of a shorter way of doing that is by implementing, taking out this brackets here, because this is actually only one little line right there. Now, so now we can actually instantiate a Paris hat and then call the method trick on it, and it'll print out sit. But there are devious illegal hats out there. So how are they going to cause some problems? Well, let's see. Someone declares a file called illegal.scala. So in illegal.scala, they can create a case object, illegal hat extends hat. So what's happening there? Well, this can now be called. You can create an illegal hat, print line illegal hat.trick. That's going to break our program. That's not good. So if you have a very large program, people can extend your trait anywhere in that. You're not going to get exhaustive pattern matching, which gives you that compile time error that we're comfortable for. So we're going to use something called seal. So that lets us seal our trait. So you just put this keyword seal in front of it. And then you're able to stop anyone from extending that outside of the file. So it means that in here, case objects can only extend it in the same file there. Now we have exhaustive pattern matching because we know that all the case objects that extend it are only ever inside that one file. So turns out advertising hats and anti-fountain trails was a great idea. So we're now pivoting to fruit hats. The fruit hats, they now carry a fruit of some kind inside them. So we've got case class Paris carrying apples inside there. So we're now they're not case objects anymore because we need them to hold data. So we're declaring them as a case class. The case class is we can define whatever we want inside there, just make it back to the data and extend hat, just like with a case object. And then we can define a new function for eating hats. So when we pattern match on a case class, we can also pattern match on the data inside that class. For example, if there's 2 apples inside there, we can pattern match and say, okay, Paris of 2, return Paris of 1, you ate 1 apple. But you can do that a little better. You can actually declare a variable there by pattern matching on Paris and declaring the first variable to be a number of apples, and then returning Paris with the number of apples minus 1. So we can do this with any number of variables. It's relatively straightforward. And then we have case Nice. It's still an object, so we're not going to include that in there at all. And we can just transform that to a Paris hat with 5 apples if we want. And then we have something a bit curly in here. So case Marseille at Marseille underscore. So let me kind of dive into what's happening here. First of all, you're matching on Marseille. You've got Marseille, and then you've got underscore here. That underscore says, I don't care what the first variable is. Then the second thing you're doing is you're saying Marseille at Marseille. So what you're saying is, I'm going to declare a variable called Marseille. It's going to be whatever you matched on here. That's getting passed over that arrow over here. And then you're saying, okay, return that variable. And that's going to return Marseille. So you did all that to do nothing, actually. And I guess it's a kind of a drawback. You have to explain that a little bit further. All right. Okay. So final summary of all of that. I guess the key takeaways that you want to get here is that in Scala, you want to use case classes to wrap data in a sensible manner. You want to use companion objects to hold constructors and static functions. And then you want to use sealed traits to create types with multiple possible permutations. And always that file program. Done. Okay, questions?
There might be some questions in there.
Yes. Good point. What are some common FP patterns in Scala? Okay, so I guess the core thing about FP, it's got a couple of rules. One, everything is immutable. So you will see that all of the variables are by default declared as immutable, especially in those like case classes and things, unless you specify for them not to be. You can actually use something called bar. So instead of declaring something, as val, just use bar. This makes it totally immutable, but it's generally frowned upon. Another common FP pattern, the reason we use objects so much is kind of to make sure that we're putting like bags of functions in places. So the thing is, functional programming, so unlike object-oriented programming, which is supposed to be classes, and a class is just like a functions and data mixed in together. When you declare these objects, you're able to just declare a whole long list of functions and then chuck things into there. Does anyone else want to mention any other patterns that come to mind?
The core, there's like heaps of patterns and all sorts of patterns. The key difference between traditional imperative or object-oriented programming is you think in terms of data and functions. So your whole program, one big function posed at a smaller functions. So that's why you see things like case classes so much, because we care about data and functions as opposed to statements on or objects. It's all about starting from your input and then applying a bunch of functions to that input so you end up with wrap. That's pretty much the core function.
Oh man, there's a lot of typos in that. I tried to get so many of them out, but I can get all of them. I actually have no idea. Should we like Google that? It's fluffiness. There you go. Done. If I'm working for a lava sheet, yes. Oh man. Yeah, I actually was told. Someone would mention that to me. They're like, "Oh, yak shaving thing in there. This is definitely a throwback." Yeah, it's kind of a reference. That's fun. Now I wish I thought. Okay, so when is the last? This is my favorite thing about anonymous submission. Where did my OG llama go? I shaved him now. That's functional programming for you. And we're done. Okay, cool. That was fun. Are there any other questions?
Each when you go back a couple of slides. Your last code example. Yeah, so here where you've got, so each hat is going to get called like as a function, right?
Yep.
And
Right.
So like
Toulouse, I can't match up what the case is going to be with different arguments and things to the EPAD function. Could you give an example, like show how that might be called?
Yeah, sure,
what that
sure.
would look like?
Okay, so it's on the whiteboard. So okay, you've got your hat, right? You might say, you know, our hat equals. So you have to actually instantiate the case class. So you know, you can then say Paris and then say have 5 apples, yeah, right? And then you go about new hat equals hat eat hat. And then it goes, you can say, yeah, and then you just do that without actually putting anything like the actual defined variables. That's going to return us a new hat. So it's going to be our Paris hat minus 1 apple is returned from that. Does that kind of make sense? So you declare the hat, you can say equals Paris, and it's just like declaring a case class. Because what you've actually done here is you've made a case class that just happens to extend hat. So you're using exactly the same as a case class that just has this method inside it. So in the llama, you would then add on to the case class llama, you'd have your like strength fluffiness name, and then you'd say hat at the end, hat of type hat. And then in the llama, you could define a function that would then print out like, oh, you ate one thing from the house.
Yeah.
Does that make sense?
Yeah, I think so. I'm probably thinking very, is it kind of like we've inherited from a bunch of different things, rather than defining new methods in each of your inheritance?
That's exactly what we've done.
You've got one place to do it.
Yeah, so when we say extends hat, it's like it was an interface or a superclass.
Yeah.
And we've now taken that and we get all the stuff that's in it. So all the methods, for example, that method, you know, eat hat comes with it. That's pretty much it. It's a little bit, yeah.
it's an interface, because so you can inherit from multiple traits, but there is also an abstract class.
Exactly. So if you can say extends hat, and then if you want to put other things on it, like shoes, you can say extends hat with shoes, and then you can just keep adding in whatever more things. So if people are familiar with Ruby, might know mixes as well, adding however many traits you feel like, which is kind of the strength of it, instead of just having comparison with one class. Right. Okay, cool.
It's like chicken.